All right. Hello, everybody. Okay, so this is a pretty exciting lecture because now we're able to start actually computing solutions of partial differential equations in Matlab, which is awesome. So just a show of hands, how many of you have solved a PDE before on a computer? I see two. Any more than two? Okay, so this is going to hopefully be pretty interesting. Let's see, a couple of logistical things. So I just posted solutions to homework 1 and homework 2. And then I realized homework 2 is not due until this afternoon, so I took homework 2 down. But it'll be due, I'll post the solutions like sometime this weekend. So if you absolutely need an extension on this homework, you have to tell me now, like immediately, or else I'm not going to take any late homeworks. Because I'm going to post the solutions today so you can like see them. I was going to post a homework 3, but I think I'm going to do it after Sunday. Because I don't want anyone to do anything except focus their energy for the Seahawks winning. All right, and I've also posted all of the lecture notes up to date. And everything through today's lecture is fair game for the midterm. Okay, and the midterm will be handed out on Wednesday. By handed out, I mean it'll be posted here on this website on Wednesday after class. Okay, it's a take-home exam, same rules as last time. Any questions at all? No? Okay. All right, so this is pretty exciting because I'm going to start to get into a few really important concepts today that I hope are things that you take with you for a long time. So in the last 2 lectures, we solved Laplace's equation analytically by hand, right? And it was kind of messy, right? We got a bunch of sines and cinches and an infinite series, which seems pretty nasty. And so what we're going to do today is we're going to show that the expression we derived is actually pretty simple to implement in Matlab. So we'll be able to, the cool thing is we'll be able to solve this heat equation on a rectangular domain with arbitrary boundary conditions. So these could be any nasty function that you like of temperature on the boundaries. I'm also going to show you how to solve this Laplace's equation without any analytic formulas, like without any cinches or sines. We're just going to do it purely numerically, just like we solved numerical ODEs using ODE 45. We're going to cook up schemes to solve these PDEs numerically. Okay? What else am I going to do? Yeah, and this is really important. We're going to start introducing the concept of Fourier transforms today. And this is all that I'm going to talk about next week are Fourier transforms and how they're useful in PDEs and how they're useful for representing functions like our boundary conditions in a nice way in terms of sine waves. Okay? All right, so we're going to solve Laplace's equation numerically on the computer. And there's a couple things we can do. So I'm going to give you like 5 or 6 different options for solving this. We're going to try them all out in Matlab, and we're going to see which ones work best. Okay, so numeric solution to Laplace equation. Okay, so just remind me, what is Laplace's equation? Del squared u equals 0. Okay, so if this was a function of 2 variables, this would be partial squared partial x plus partial squared partial y of u equals 0. Okay, and this is a linear operator. All right, this is a linear operator in u. So if I have 2 solutions, u1 and u2, then their sum is also a solution. Okay, so the first technique is actually kind of interesting. So what we're going to do is we're going to use the heat equation, UT equals some constant del squared U. And we're going to try to solve this iteratively. We're going to start with some initial condition, some initial guess, and we're going to iterate it forward in time. And we're actually going to let the heat equilibrate using the heat equation, right? Laplace's equation is the solution as time goes to infinity of this equation with alpha positive constants. Okay? So how can we solve this kind of a PDE on a computer? What general approach should we take to solving these things on a computer? Something like a Newton-Raphson. For which part? For this part? Or for this part?
The U of T part.
The U of T part. Okay. Okay, so we have this U of T part and this del squared U part. We're going to need some way of representing both of these. Maybe I should ask a more basic question. How are we even going to represent the solution in a computer? Sorry? Well, what do I want out at the end? I want a movie. I want to see my heat distribution evolving in time to some equilibrium. And what is that movie going to have? It's going to have frames in the movie, and each frame is going to be a rectangle, right? With colors. So what I want is U to be a matrix. Okay, U is going to be a two-dimensional array in Matlab. It's going to be a big array of numbers. Okay? And I'm going to try to update that array of numbers using this essentially differential equation. This is like an ODE for every single little grid cell in this array of numbers. Okay, so I'm going to have this two-dimensional array of temperatures at every point in x and y. And I'm going to figure out how at each point x and y, how does that little grid cell's temperature change as a function of its neighboring grid cells. Okay? So the first crudest thing we can do, so this U is like this big kind of array-looking thing, right? Like it's a big matrix or a super tall vector, if you want to think about it like that. So the crudest approximation to this time derivative, what did we learn from 564? What's the simplest first derivative we can take? Sorry? I heard Euler. What else? Like a forward difference. So we're going to say that this is U at time t plus delta t minus U at time t divided by delta t equals alpha Laplacian of U. And I'm basically going to take an initial condition U at time, this is U at time t. I'm going to take some initial condition at time 0, and I want to step it to time 1, time 2, time 3, and so on. So what I want is U at time t plus delta t as a function of the previous time step. So that's equal to U plus alpha delta t Laplacian of U at time t. So this defines an iteration. If I have some initial guess U naught, U at time 0, then I apply this formula and I get U at time 1. Then I apply it again, I get U at time 2, U at time 3, ... And eventually I get U equilibrium, which is the solution of Laplace's equation. So this isn't anything super fancy. We're just doing what we've done before in 564 to solve this ODE. Okay, I'm thinking of this equation as a really big ODE with m by n ordinary differential equations. So let's say that there are maybe L by H. So I'm going to have L by H ordinary differential equations, and this is the formula to iterate all of those ordinary differential equations forward using forward Euler. So forward Euler is the crudest thing we can try. But it's going to work, which is kind of cool. Okay, does this make sense? Okay, so what's the next thing we have to do in this equation? So we've figured out this term. What's the next hard part? Yeah, how do we figure out what this Laplacian of u is? So what is the Laplacian of u? Okay. Partial squared u with respect to x squared plus partial squared with respect to y squared. Okay, so at every single grid point, at every ij grid point here, I and j are indices for my grid points. They go from index 1 to L, 1 to M. Do we know how to compute these partial derivatives? Yes. Okay, how do we compute these partial derivatives? So first of all, there's a really easy command in Matlab called del2. So del2 will compute the Laplacian of my matrix. Okay, so this is the easiest and most accurate. But I don't really know what del2 is doing under the hood, so I'm going to tell you how we would do this by hand if you had to. So how would you compute this derivative by hand if you needed to? Right, you would take finite differences in the x direction to get the second derivative in x, and finite differences in the y direction to get your partial derivatives in y. And this is essentially, this method is called a stencil. It's kind of a cool idea. So let's say that I have my domain with all of my data points. Right, this is a big array. Let me just write all these down. Let's say that this is my large rectangular domain. And so the idea is, if I want to compute the partial derivative, the Laplacian at this point, I can essentially do that by considering finite differences with its neighbors. Okay, so this is what we're going to do. We have so let's call this the ijth point. And if we want to compute the Laplacian of u at the ijth point, we're going to use this 5-point stencil, meaning we're going to use the data from the 5 points around it, from it and the 4 points surrounding it, its nearest neighbors. Okay, this is called a 5-point stencil. Okay, and it's actually super duper easy to figure out what this derivative should be. You can also figure out how accurate the derivative is. You can cook up higher order accurate schemes using 9-point stencils and 18-point stencils, or there's all kinds of fancier ways of doing this if you take a larger and larger window to compute these derivatives, just like we did in 1D functions. Okay, and the formula is pretty simple. So this is ij, this is I plus 1j, I minus 1j, ij plus 1, and I j minus 1. Okay, so what is my partial derivative? What's my first derivative? Okay, I'm just going to write it down. So first I'm going to do my partial derivative in x. Okay, so partial u partial x is ui plus 1 j minus ui j divided by delta x. That's this partial u partial x here. I'm finding the first derivative using forward difference. And then I'm going to subtract the first derivative using backwards difference and divide by delta x minus uij minus ui minus 1j divided by delta x divided by delta x. And this is the second partial derivative. I'm basically just computing two first derivatives here. And then I'm taking the first derivative of those first derivatives. That's what this is. And you can work it out that this is really, I mean, we've done this before. This is just the second order central difference that we derived in the last quarter. Okay, you can do a similar thing for partial squared u partial y squared. That's basically the same stuff, except instead of varying the I index, the x direction, we're going to be taking this along the y slice by varying the j index. So pretty straightforward. We have u of I j plus 1 minus u I j divided by delta y minus u I j minus u I j minus 1 divided by delta y divided by delta y. And so let's just get rid of this and write out what the solution is. So I'm going to assume that delta x equals delta y. And I'm going to add these two things up to get the Laplacian. So my Laplacian equals 1 over delta x squared. I'm assuming delta y is equal to delta x. 1 over delta x squared times, okay, what do I have? I have a positive value of this point. That's here. I have a positive value of this point, a positive value of this point, and a positive value of this point. So these 4 points, I have a positive value of u I plus 1j plus u I minus 1j plus u I at j plus 1 plus u at I j minus 1. And then I have 4 negative copies of u in the middle. I have 4 negative copies of my central point at index ij. So minus 4 u at ij. Okay. So this is a really simple formula. If I had a function defined on this array, if I had my temperature distribution u0 or u1 or u2 or whatever, then I could compute its Laplacian using this formula, and I would just write a huge for loop through I, all the i's and all the j's. And I would have the Laplacian at every point. This only works for interior points. Right, this function has I plus 1s and j plus 1s, so it only works for the middle points. Okay, should we code this up and try it? I think we have all the ingredients we need. We know how to compute this iteration in time. This is time. And we know how to compute this Laplacian of u if we have an array, a rectangular grid of points. Okay, so we're ready to code this up. All right, let's try it again. Okay. This seems like it should go farther down. Let's try that for now. Okay. Okay, that works for me. Okay, so what we're going to do, we're going to solve the same basic setup that we had derived an analytic solution for in last class. We're going to have a rectangle, and this rectangle does not have to be square, but I'm just going to make it square because why not? So it goes from 0 to L, 0 to H. And it's going to have 0 temperatures on the top and bottom. It's going to have, we could do anything. This is completely general, but I'm going to have it have a temperature fixed at 1 on the left and the right. Okay? We could do something else if we wanted. Okay, so I made a color map for the Seahawks just this morning on my bus ride over. People thought I was crazy. And this is what the iteration looks like in time. So I'll just show you what the solution is, and then we'll walk through what all the math does and what all of this means. But what we have is an imposed temperature on the left and the right walls equal to 1. Okay, and we see that for long times, our temperature is 1. We have an imposed temperature of 0 on the top and the bottom, which is also satisfied. And as time is evolving, we have our temperature kind of diffusing into the middle where they're meeting. Okay, which is kind of what we expect to happen. It looks so much better on my computer screen that it's kind of irritating. Let me see if I can make this larger. Okay, I can make a figure, and I can set my position 100, 600 by 600. Let's see if this works. But I lost my Seahawks color. Let's try again. Okay, and I bet I can make it 800 by 800, maybe 7 by 7. All right, I'm killing all the lights. Does that help at all? Okay, so you can see these kind of ISO contours that are in the middle. And if you could see a little bit better, you would see that there are these kind of hyperbolic-looking level sets of this function, which makes sense because our solution has hyperbolic sines and cosines. That doesn't help. Okay. All right, so that's what the solution looks like. Now let's go through and figure out how we actually coded this up. So I told you there were a bunch of options, right? The first one was to use, okay, let's just start from scratch. So the first thing I do is I create a 100 by 100 square, and I say that my temperature distribution starts out being 0. Okay? And what I'm going to do is I'm going to iterate my heat equation 2,000 times. For 2,000 dTs, I'm going to iterate my heat equation. So this should come into equilibrium. And every single one of these iterations, the first thing I'm going to do is enforce my boundary conditions. Whatever happened to mess up my boundary conditions, I'm going to rewrite over that. And I'm going to say, no, the temperature is fixed at 0 on the top and the bottom, and it's fixed to be 1 on the left and the right. Okay, so I'm manually fixing my boundary conditions by just overwriting those numbers in the array with the 0s and 1s. Now, technically, I don't think I have to do this. I think I could bring this whole thing out, and it would work. Okay, good. So I wrote this code correctly. Okay, so I'm not ever changing those boundary conditions. Okay, so inside my iteration, I do the following thing. The first thing I do is, every 10 iterations, I just plot the thing. So we're seeing this. It's doing 10 dTs, and then it plots. 10 more dTs, and then it plots. It gets really slow if you do it otherwise. So this is just plotting. And option 1, I'm using the del2 command to compute my Laplacian. Okay? I told you that there's this function del2, and it computes. Remember, we had uk plus 1 equals uk plus delta t alpha times the Laplacian of u at time k. So there's a function in Matlab called del2, and it computes the Laplacian of u. Now, I call this L of u because this is a linear operator in u. L of u is usually what I use for linear operator. So this is L of u. Okay, that's this line here, 34. So I compute my Laplacian using this slick Matlab command. And now what I do is I take all of my interior points here in the middle. Let me get a little marker. So I take all of my interior points and I iterate them forward using this, this formula. Okay, so I evolve. I know that my boundary conditions aren't changing, so I don't need to change them in time. I'm fixing them. And so all of the interior points, once I've computed this Laplacian, I update them with this formula. Does that make sense? I take my old solution plus some constant times the Laplacian of u. So I say all of the interior points from 2 to L minus 1 and 2 to H minus 1, all of the interior points are going to equal their old solution plus some number times my Laplacian. Does this make sense? Yeah? Does this not make sense to anyone? I can go through it more carefully. Right? This is a big array, and this is a big array. And those correspond to u at my last time step and my Laplacian of u. Okay? Now, what if I made this constant delta t times alpha larger? Right? Maybe I want this to converge more quickly. I want my heat equation to be more aggressive. So I'm either going to have more thermal diffusion or I'm going to have a larger time constant. Those are the two ways I could do it. So let's say I make this 2 times the Laplacian of u. What do we expect might happen to this equation if I make dt or alpha too large? Say it again? Well, it could converge faster, or it could go unstable. Those are the two options. It's either going to converge faster until it doesn't, and then it'll diverge to infinity. So let's see what happens when I make this larger. Okay, so notice now that this is essentially, this is 10 to the 300, right? That was a huge number going to infinity. It's still diverging. Let me make this a little smaller. Okay, so what we notice is that very quickly the numbers get extremely large and we have this weird instability growing. Okay, and so this iteration becomes completely unstable. I have this weird checker pattern. Anyone know why this is a checker pattern starting from the corners? Any guesses at all? So the corner is the most tricky point. That's true. Like these corners are where you have almost an infinite, kind of derivative. What else could possibly be causing this? So this checker pattern corresponds to the highest frequency sine wave that you could possibly have on this discrete grid. Okay, it's the highest frequency sine wave in both x and y. And it turns out that that wave number, that frequency, if I took this partial differential equation and Fourier transformed it, I would still have a differential equation. And the differential equation for the highest frequency wave number is the most unstable. So it's growing the fastest. And when I plot it, all I see is that one ripply super high frequency pattern. So we're going to understand this a lot better next week when we look at Fourier analysis. But we're starting to see sine waves here. This checker pattern, to me, says really, really high frequency sine wave is unstable. Okay? So we're just going to tone this back down to a reasonable constant of 1. That's as good as we can do. Okay? Well, you can do a little better, but that's basically as good as we can do. Okay, so that was one option, was just to use the del2 command to compute this Laplacian. But I spent all the time explaining this 5-point stencil, so I want to implement this 5-point stencil. So instead of just computing the Laplacian using del2, I'm going to compute the Laplacian for every point I and j using the stencil we talked about. Okay? So for all of the interior points in both x and y, for I 2 to L minus 1, j 2 to h minus 1. This Laplacian at point I, j is going to equal this formula that I derived. And I'm just going to assume that delta x equals 1, because I don't want to think about it. I don't want to normalize anything or divide by delta x's. So I just have minus 4 of u in the middle plus a positive u at each of its neighbors in the plus sign. That's it. And then I do the exact same numerical iteration scheme. Right? I do the same forward Euler time step to iterate my u solution forward in time. Now notice that I need a smaller integration factor here, because this is actually less numerically stable than this del 2. Del 2 is more accurate than this crappy 5-point stencil. And so this, I have to take really small time steps or else my error blows up. We'll look at that in a minute. OK, so now we're doing this option 1b. We're using a 5-point stencil. Basically, we get the thing we want. Doesn't look like it's changing much on the screen, but a lot of interesting stuff is happening. So I encourage you to actually run this code on a computer screen. OK, does that make sense? How we're essentially now all we're doing is computing this Laplacian ourselves. And we're doing kind of something silly that's not as good as what Matlab's doing. Matlab is actually probably taking the Fourier transform, and its Laplacian is much, 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 much more accurate than ours, which is why it's so much more numerically stable. Another option is to do something called an 8-point stencil, which instead of looking at just the 4 nearest neighbors, I look at my 8 nearest neighbors. And basically, I say that my middle point, minus 8 of my middle point plus 1 positive value at each of these 8 neighboring points. So this is an 8-point stencil. There's all kinds of stencils. There's a whole pretty interesting theory about these stencils. There's books written, Wikipedia pages. But for our purposes, we get the same solution every time. And I like del 2 because I don't have to type any for loops. For loops are terrible in MATLAB. So del is way, 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 way better. OK, please interrupt if there's any questions at this point. Does this basically make sense? OK, there's another thing we can do. So I told you that option 1 was to start with the heat equation and iterate it forward, right? Another thing we can do that's actually it makes a lot of sense, is I can take my stencil formula and I can just try to make Laplace's equation true at every time step. So option 2 is try to manually enforce del squared u equals 0 at each iteration. So for example, in my 5-point stencil, we know that our Laplacian looks like the following. We have Laplacian of u, at the I, jth grid point, equals, well, it equals something like 1 over delta x squared times minus 4 u at ij plus u at all of its neighbors. Right, these are my neighbors. So I could make this manually equal 0 in a pretty simple way. I could just set this thing equal to 0 and solve for my function at ij. I could say u ij, and I'm going to get rid of delta x squared. In my simulation, all of these delta x's are 1. So this is just equal to 1/4 times the sum of all of my neighbors. Now, what does this formula look like? What is 1/4 of the sum of the values of all of my neighbors? The average. I'm literally taking my neighbors and I'm figuring out what their values are and I'm averaging them and overwriting u. I could do the same thing with my 8-point stencil. I could have 1 over 8 times the sum of my 8 nearest neighbors. Okay? This is a perfectly valid way to solve Laplace's equation, and we could iterate this forward, and this will converge towards the true solution. Okay, so that's option 2. I'm going to code this one up now. Really glad I pre-coded all of this. Okay, so option 2 is we're going to forget the heat equation. We're going to iteratively try to make Laplace's equation equal 0 with our 5-point stencil. So what I'm doing here now is I shouldn't have called this L of u. But now I have my average function of u. This is the average of all of my neighbors. It's just 1/4 of the sum of all of my neighbors. And now all of my interior points at every iteration, I just set them equal to the average of their neighbors. This seems like incredibly simple, but it works. Okay? Totally works. Okay, so we are solving PDEs numerically in Matlab right now. Okay, we have the tools to solve Laplacians and DDTs. If I put in some nonlinear stuff, you could solve those too. This is not the best way to solve PDEs numerically, but this definitely works. Okay, this is a starting place. We can actually do something now. Okay, and we can start to have more interesting boundary conditions too. So for example, I'm going to have this new boundary condition where on my right-hand portion of my square, I'm going to impose a sinusoidal temperature distribution. Okay, just a sine 2 pi 1 to L over L. Oof, that doesn't work. Let's see. I have to do something. I commented out all of my options, so I'm actually not solving anything. I did this a lot of times in my office, so okay. So this is what the heat distribution looks like as it evolves for a sine wave distribution. So you have plus on the top, minus on the bottom. And you can see that these are just getting kind of wider and wider and wider as they encroach on the domain. But the 0 temperature boundary conditions out here are essentially bleeding away a lot of that energy. Okay? Kind of cool. You can do any temperature distribution you like, no problem. Okay. Okay, that's what I want to show you for now in MATLAB. There's more I want to show you if there's time. So that's how to code this up using finite differences. This is the crudest thing we could do. We did forward Euler and central difference for the Laplacian. Very, very crude, but it does work. We're going to figure out much better ways to solve this using Fourier transforms. So even in computers, we would like to solve this in the Fourier frequency domain. It's much easier. But first, what I want to do is I want to show you in our example from last class, we actually derived an analytic solution to the temperature distribution for an arbitrary function of y on the right-hand side. Right? We had this huge, nasty expression. We spent 2 lectures finding it. And so what I want to do is show you that you can also code this up in MATLAB, and it's actually a useful quantity. Okay? So I believe what we had was u of x and y equals the sum from n equals 1 to infinity of an sine n pi over hy sinh n pi over hx. And this an was pretty nasty. We had an equals some horrible expression like 2 over h sinh blah, 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 n pi L over, this is terrible, integral 0 to h f of y times a sine wave in y dy. Okay? Now this looks terrible, but it's actually not terrible. These are all numbers. H is a number, L is a number, N and pi are numbers, 2 is a number. These are all numbers, okay? In Matlab, we can solve this super easy. Now let's try that example that we just did, where we have this sine wave. So f of y equals, and it's not just a sine wave, it's sine of 2 pi y over h. It has exactly one period from 0 to h. So it's 2 pi y over h. That's my function of y. Let's try to plug this into here and see if we get something that's simple. Okay, so what's the first thing I need to do? Sorry?
Find a function for a.
I need to find these a's. These a's are, like, basically if I have a's, then I can plot this u. I have this u. So I need to find all of these a's. Now, what do we know about, if I plug in a sine wave in here, what do I know about how it integrates with other sine waves? So this was a homework. This is why I gave you that weird homework about integrating sine waves. This will integrate to 0 for all frequencies n except n equals 2. So a, n not equal to are all 0. A of n is equal to 0 for all n that's not equal to 2. And a2 is actually kind of simple. So it's equal to 2 over h sinh of 2 pi L over h. This is just a number. Integral 0 to h of sine 2 pi y over h squared dy. I can integrate this in Matlab, and I'll get a number out. And then that number, I can multiply it by this single frequency in space x and y, and I get my function u. Kind of cool. So let's do that. Yes. All right. Okay, so I have this L11, Lecture 11, Analytic Laplacian. Same deal, I have a grid from 0 to 100, 0 to 100, or maybe 1 to 100, 1 to 100. L is 100, H is 100. I create a big mesh grid for X and Y. I start out with a 0 temperature distribution. And what I'm going to do here is I'm analytically solving for the temperature distribution. There's no iterations, there's no heat equation, no discrete Laplacian. I have my boundary condition function. This is my f of y. It's just 2 pi y over h. This is my variable y. It's a vector of y variables. I have my constant a2, which I can solve exactly how I wrote it here. And then my u function is just a2 times sine of that frequency in y times sinh of that frequency in x. And I'm going to plot it. Super simple. And I get my temperature distribution like that. No iteration. This is the infinite time Laplace temperature distribution. It's also, there's no numerical error here. This is completely, I mean, except for the machine precision of sinches and sines, this is exactly the right answer. And it was really simple to solve. In Matlab, all of these nasty integrals and functions are easy. They're just, sums and sines and sinches. Does this make sense how we did this? Okay, I want you to look at this code if it doesn't. This is important stuff. What if I had a nastier boundary condition? What if I had a nastier boundary condition that wasn't just a nice sign? Then what would we do? What if f of y was not a nice single sine wave? Then I would have to just integrate over it a bunch of times. I would have to compute this a n a bunch of times. I'd have to compute it for n equals 1, 2, 3, 4, 5, up to maybe 100. And I'd have 100 of these sines and sinches that I'm adding up, but I know what the coefficients are and I know what the frequencies are, so I can do that. So the last example I'm going to do, and by the way, this is exactly like numerically taking the Fourier transform. So the last thing I'm going to do, this is my hard analytic Laplacian, is now I'm going to solve this for the boundary condition we did earlier, which is 0, 0, 0, 1. This is a hard boundary condition for sines and cosines. So this is my function of y. It's just 1 at all of these 100 points. My boundary condition is just a big vector of ones, 100 ones. And now what I'm going to do is I'm going to take my temperature distribution, set it initially equal to zeros, and I'm going to add up a 1 times sine of the first frequency, sinh of the first frequency, plus a 2 sine of the second frequency, sinh of the second frequency, and so on for k equals 1 to some number. Let's try, okay, I'll show you the final answer. I'm going to add up all 100 of these Fourier modes. And I get exactly the right temperature distribution that I would expect. We could verify this using our other code. In fact, why don't we just do that? Take our other code and so our other code iterates eventually to the same solution. Except this has a bunch of numerical error and it's kind of crappy, but basically this is what it's supposed to look like, is some kind of weird shape that's bleeding towards the left. But we can get it almost instantaneously here by adding up these 100 sine waves. And this is the infinite time distribution. This is actually much more accurate. So let's see what happens if I just have the first mode. Not terrible. What about the first 5 modes? Interesting. I wish you could see this a little clearer. It gets bright, then dim, then bright, then dim, then bright. It's beating. Weird. Let's try the first 10 modes. That's interesting. It gets bright, dim, bright, dim, bright, dim, bright, dim, bright, dim. That's like 10 switches. I'm having 10 modes. If I did 20, it would be a little bit better, until eventually I have enough modes that that alternating pattern is smaller than my dy. Okay? So the basic idea here, this example is completely designed to motivate Fourier transforms. The idea is that I can have an arbitrary function, completely nasty function, and what I want to do is I want to find these a of n equal, all of this stuff. I want to find the coefficients of that function in a sine wave basis. I want to decompose my function. I want to rewrite my function as a sum of sine waves of low frequencies to high frequencies, of various frequencies. So this is essentially where the Fourier transform comes from, is writing my function y, my function of y, as a sum of sine waves. It's now a function of frequencies, okay, these a's. And if we can do that, then we can solve all of these PDEs numerically, very quickly, very accurately. And we can solve them for nasty geometries and much harder equations than just Laplace's equations. Okay? So this basic idea is what we're going to use to introduce Fourier transforms on Monday. That's everything I have. Have a great weekend, and I'll see you on Monday.